Cruising at 70 miles per hour, your car is a massive 2-ton kinetic system held in a state of delicate mechanical equilibrium. Every second you spend on the highway, thousands of controlled explosions inside the engine block generate sheer rotational force. Your car's engineering is designed to absorb that immense physical stress, so you never feel the chaos happening underneath you. But that illusion of smoothness can shatter instantly. It begins as a subtle shudder creeping into the steering wheel, or a deep vibration radiating through the driver's seat. Most of us react by turning up the radio or gripping the wheel a little tighter, dismissing the shake as a stretch of rough pavement or a minor comfort issue. High-speed vibration is never random. It is a physical alarm bell signaling that the machine's mechanical equilibrium is failing. When you're moving 70 miles per hour, that shake is the first sign that 4,000 pounds of steel and glass are no longer moving in harmony with the road. To find the source of that shaking, we have to look at the primary source of the car's rotational mass, wheels and tires. A flaw as small as a fraction of an inch, like an uneven tire wall or bent rim, disrupts the wheel's geometry. Spun at highway speeds, rotational physics magnifies that flaw, striking the pavement with violent, repetitive force hundreds of times every minute. This repetitive hammering creates a destructive ripple effect, transferring kinetic shockwaves directly upward from the tire's contact patch and into the vehicle's chassis. Those shockwaves immediately assault the suspension system. Parts like the shocks, the ball joints, and the tie rods are designed to maintain the car's alignment geometry, keeping the wheels pointed exactly where they need to be. But continuous, high-frequency vibrations force these components to work beyond their design limits. Over time, the rubber bushings tear and the metal joints wear down, physically warping the car's geometric balance. This localized tire issue spreads through the mechanical connections, actively dismantling the vehicle's entire lateral stability system. While wheels are the most common culprit, vibrations can also originate from the vehicle's friction-based stopping system, the brakes. When you press the brake pedal, flat brake pads clamp a spinning metal rotor. If warped from heat, the pads cannot maintain smooth contact. This uneven contact generates intense, localized shaking that shoots directly up the steering column. Other times, the source of the vibration is found at the center of power generation, deep inside the vehicle's engine bay. Your motor sets on heavy-duty rubber engine mounts, designed to absorb the raw explosive force of the cylinders. When a mount fails, that shock absorption barrier disappears, allowing the engine's natural movement to rattle the metal frame of the car. Whether the violence is generated by braking friction or horsepower, internal mechanical failures bypass the vehicle's dampening systems and transfer kinetic energy directly to the driver. Constant shaking introduces a dangerous physical gap. It can actually lift the rubber off the pavement. You can see daylight between the tire and the road hundreds of times a second. Because the tire is no longer maintaining a stable contact patch, the vehicle's braking distance increases and steering precision drops, leaving you with less control during an emergency maneuver. This mechanical instability is compounded by the physiological toll on the driver. Enduring continuous, low-frequency shaking induces acute fatigue as your body constantly tenses to compensate for the movement. This physical exhaustion directly increases your reaction times at the exact moment when the vehicle's margin of error has been narrowed by mechanical wear. Defensive driving requires recognizing high-speed vibration as an imminent risk signal. Safely reducing speed and seeking professional diagnostics is the only way to prevent a minor imbalance from becoming a catastrophic loss of control.